Assalamu alaikum everyone. So we'll start our new lecture on reverse curve. So up till now we've covered simple circular curve and a compound curve, which was combination of two or more simple circular curves of same or different radius. And now we are moving on to reverse curve. So reverse curve is again a combination of two simple circular curves, but these simple circular curves are in the opposite direction. So this is usually given when you want to join two roads or two paths which have a very small angle between them, or the two are parallel to each other. So, for example, uh, so usually we get to see this sort of condition when we are trying to connect roads in hilly areas, because usually over there you are bound to give these sort of curves because you don't have that available land. And in the other case as well, when you have, let's say, these two roads and you want to connect this point with this point over here, but in the end, the direction would remain the same, right? So you would be traveling in the same direction even after going on to the other path. So this usually happens when you don't have available area over here and you want to change the direction in which the road is traveling. And obviously, you cannot join these 2 points with a simple circular curve because that would mean that once you get to this point, your actual mode of travel should be in this direction, like you have a U-turn, right? But in this case, even after the curve, you would be traveling in the same direction. So in that case, we give a curve which is called as a reverse curve. So a reverse curve is basically combination of two simple circular curves. So one simple circular curve over here and another one over here, but the two are in the opposite direction. So if you draw their center points and draw up their radiuses, so you will see that their centers lie on two opposite sides. So this is a reverse curve. Now it can be given when you want to join two roads which are parallel, or it can also be used if the two join like this. And in that case, you can also give a simple circular curve. So it depends if the two are parallel or if they are non-parallel. So we will study these cases. So like I said that a reverse curve consists of two simple circular curves of equal or different radius. So the radius can be equal or they can be different, but they turn in opposite directions with a common tangent at the junction of the arcs. So what this common tangent is, we'll get to that. So this reverse curve is also called a serpentine curve because of its unwinding sort of a direction, or uh, a very zigzag, you could say, type of motion. Because if you're traveling on this curve, so you'll be traveling along a curve in one direction, then you would have to completely change your direction at the midpoint towards another direction. So in that sense. So reverse curves are generally used to connect two parallel roads or railway lines, or when two lines intersect at a very small angle. So we have discussed this. And the curves are suitable for railway siding, city roads, but they should be avoided as far as possible for the following reasons. So they say that these curves should be avoided. Why? Because number one, super elevation cannot be provided at the point of reverse curvature. So if you remember what super elevation is, in super elevation, you raise the level, reduce level of the outer edge of the curve so that when the vehicle or anything is traveling on that curve, there is no chance of that vehicle to topple. So that is super elevation. But if you can imagine a reverse curve, the super elevation would change. On one curve, it would be on the exterior end towards the right. On the other curve, it would be towards the exterior end on the other direction. But at the junction of the two curves, there would be no super elevation, right? So in that sense, because you cannot give a super elevation, so that means the chances of again the vehicle toppling over is more at the junction of the two curves. Number two is a sudden change of direction would be dangerous for the vehicle. So, like I said, if you imagine traveling on this curve, you would have a sudden change of direction, and you had to put up a lot of signboards and everything to show that after a while there would be a reverse curve, and you were traveling in such a particular or a unique direction. A sudden change of cant causes discomfort to passengers. So, cant is slope. So, like we discussed in super elevation, that on one curve you have super elevation on one side, on the other curve you have it on the other side. So, that is obviously very discomforting for the passengers. Carelessness of the driver may cause the vehicle to overturn over a reverse curve. So, like we discussed, the super elevation changes on the two sides, and you have to be very careful. So, in essence, this curve is avoided as much as possible, but um, it's not possible for you to avoid it in its essence. You have to give it in hilly areas. It's inevitable. You would see a lot of reverse curves. Even in cities, you would see a lot of reverse curves, but they are avoided as much as possible. So, like we discussed, we have two different types of reverse curves depending on what the direction of the roads are. So, in the first one, what we have is that we have one road AB going in this direction, and once you give the reverse curve, your direction would become this ED. So, in this sense, if you join the two lines AB and ED, they join at the point F. So, like we do before, in the case of a simple circular curve, so you want to join two roads like this, and you give a curve over here, and they join at this point, and you have a deflection angle over here. So, similarly, when you join the 2 points or join the two lines, so you would have this angle over here, and we would call this as the deflection angle. Now, when we give the two curves, the curve would start from the point T1, it would go to the point C, and from the point C, you would have an opposite reverse curve, which would end at the point T2, and after that, T2D would be the direction of travel. Now, if you look at the two curves individually, they are again just a simple case of a simple circular curve. So, like we did in the compound curve, where we tried to analyze the two curves independent of each other, so it gets very simple. So, if you see the first curve over here, T1C, so you can say that you are trying to join two roads A, B, and B, E, and they join at the point B, and you have phi 1 as the deflection angle. So, this would become phi 1 as well, and you have R1, which shows the radius of the first curve. And this curve endpoint is at the point C, and at the point C, you have the starting point of the second curve, which has a radius of R2. So it has deflection angle phi 2, so phi 2 over here. And again, you would have these tangent lengths, and then you can draw over here a long chord. So the things that we do usually. But what's different over here is this line BE, this line over here. So this is the common tangent for the two curves. So like remember, if you remember, we had a common tangent for a compound curve. Over here again, we have a common tangent for a reverse curve, which has a length of BE. And if you see how it's made up, it is just addition of tangent length of the first curve and the tangent length of the second curve. So this tangent length plus this tangent length gives you the length of the common tangent. And these things help you to find out different values for the curve if some values are not given. So let's say if radius is not given, so you can use these relations to find out the radius. Or if you don't want to lay out this curve using a theodolite, and you want to do this by using the ordinate method, so then again you would need different sort of information. So this is again just geometry, and it's better to remember uh, what different relations can be made up for the curve, because it would help you to actually determine different variables. So we've discussed these factors over here, and we'll jump straight to the case one, when the two straights are non-parallel, something that we just discussed. So over here, just a recap that phi 1 is the deflection angle for the first curve, and phi 2 is deflection angle for the second curve. And Phi is the angle of intersection. So see, this is the angle of intersection for AB and CD, which is equal to phi. So this is not the angle of reflection. Angle of reflection, if you remember in simple circular curve, it's the other angle. So if you add 180 in the angle of intersection, so it would become angle of deflection. So over here, there's change in notation, so no need to get confused about this because this won't be used in actual calculations. T1, T2 are the tangent points, and F is the point of reverse curve. So this point where the first curve ends and the second curve starts, and you have the common radius for the arcs, which is r. So that would be if the two curves have the same radius. The two curves can have different radius. In that case, you would have r1 and r2. So the different relations that we can develop are, number one, tangent length of the first arc. And if you remember the equation for the tangent length, it is r tan phi by 2. And similarly, you have tangent length of the second arc, and the length of the common tangent becomes r tan phi 1 by 2 plus r tan phi 2 by 2. So the common tangent is the distance BC, and in order to get that, you would add the length of the tangent of the first curve and the length of tangent of the second curve. So that would become the length of the common tangent. Similarly, you have length of the first curve, something that we've done before, um, by the relation L is equal to r theta. So over here you have the length of the curve r into phi, and then multiplied by pi by 180. And similarly, length of the second curve, and then we can calculate the changes. So if you are given the change of, let's say, change of the point B. So from the change of the point B, we can calculate change of the point T1 by subtracting the tangent length BT1. Once you have change of the point T1, you will add the length of the first curve, circular length, and you would get change of the point F. Then you would add change of the second curve, and you would get change of the point T2. So that's the first case. And before we jump on to the second case, first let's solve the example for the first case. So the example is that while serving along the alignment of a road, the magnetic bearings of the lines AB, BC, CD are measured as 80 degrees, 110 degrees, and 60 degrees. Now, like I told you that you could be provided by the figure or you could not. So if you are just given um, the statement of the problem, so you should be able to draw the figure. So if you read it, it says that, yeah, it says over here in the second last line that we want to connect the lines AB and CD by taking BC as the common tangent. So you should be able to draw just a straight line AB and then a straight line CD, and they should intersect at an angle. So it says that the two straights are obviously non-parallel. That is why they have given you all these bearings. And the bearings of the line AB is 80 degrees. So if you remember how to draw the bearing is the clockwise bearing or the angle from the north. So you should just establish one direction for the north. It can be arbitrary. And then by using the same north for the whole question, we can draw the entire figure. So by taking north and by drawing up a bearing of 80 degrees, and remember by bearing over here, we mean the forebearing. So the forebearing for the line AB is 80 degrees. So you draw a line in this direction. It's obviously a rough sketch. So your when you draw these, your sense of the angle should be nearly approximate. So you can't be far off, otherwise you won't be able to draw a good picture. And then we have bearing for the side BC is 110. So again, 110 over here. And then we have the bearing of the side CD is 60. So from the point C, the forebearing 60, and you have the direction of CD. Now remember that the lines that we have to join are AB and CD, right? And BC is the common tangent. So that means from the point B to the point C, this is the common tangent. And somewhere between the line BC, you would have the point of reverse curvature. So you would have from T1 this one curve and this second curve, right? So you should be able to draw this, and the length of the side BC is given, which is 200 meters, and the change of the point B is given. And they're asking you to find out all the other data. So that means they haven't given you the radius of the curves, and but they've said that the radii of the both curves may be assumed equal, right? So you would have just one R, you won't have R1 and R2. But what we know is R1 is equal to R2 is equal to R, but the value of R is unknown. If you remember from the starting lecture, I told you that in order to solve these, the information that you need is phi and R. The chainage is sort of extra. It doesn't help you in solving the question, but if they give you chainage, then obviously you have to find out chainage of the starting point of the curve and the ending ending point of the curve. But in this question, radius is not given, but we can calculate phi because if you remember what phi is this deflection angle, right? And if you see for the line AB, they have given you the bearing of the line BC, which is 110, right? Which gives you this line, the common tangent. And if you see what phi would be, phi is this angle. And in order to find out this angle, we can make use of this bearing, which is given to us. And similarly, for the line CD, we are given with the bearing of bearing of the line CD over here, which is 60. And what we are interested in is finding out this phi 2. And by making use of these four bearings which are given to us, we should be able to calculate um, phi, phi 1 and phi 2. Yeah. So if you see over here that in order to calculate phi 1, what we are given with is this bearing, which is 110, and we are interested in calculating phi 1. Now, if you see over here, the four bearing of the side AB was given, and this line is extension of that. That means if you extend this angle is 80 degrees, and this is 110. So in order to calculate this angle, what we would do is we would just subtract 80 from 110, and this would become 30 degrees. So phi 1 becomes 30 degrees. Similarly, for phi 2, what we are given with is this 60 degrees, which is the four bearing of the side CD. And what we can do is we can make use of the back bearing of the side BC. Now, if you extend this line over here, and the back bearing of the line BC would become this value. And what would this be? The four bearing is 110 and the difference is of 180. So the back bearing would become 110 plus 180, which would give us this angle over here. And from this, what we can do is that we can subtract this 180 and we can subtract this angle of 60. So this should give us the angle of phi 2. So using these, we can calculate phi 1 and phi 2. So phi 1 comes out to be 30 and phi 2 comes out to be 50 degrees. And what they have given is they have given us the length of the common tangent BC, which is 200 meters. And what we are trying to find out first is the radius. Now, in order to find out the radius, what we can do is that we can make use of the relation of finding out the length of the common tangent. So that is equal to the tangent length of the first curve and the tangent length of the second curve. So that means 200 is equal to r tan phi 1 by 2. So r tan 15 plus r tan phi 2 by 2. So r tan 25. So since radius is same, so we have just one variable in this equation, and we can find out the radius. Then we have tangent length of the first curve, um, and we were given, remember, the change of the point B, which was 950 meters. So from the change of the point B, we can minus the tangent length T1B. So we can get tangent of the point T1. In that, we can add the curve length. So that means we now need the curve length. So curve length is pi r phi 1 over 180. So radius is known, phi 1 is known. We can calculate the curve length. Similarly, by adding the curve length in the change of the point T1, we can find out change of the reverse curvature point. And in that, when we add change of the second curve, we can find out change of the end point of the second curve. So after that, we can find out length of the long chord for both the curves. And once we have those, we can find out the total, um, length of the long chord for the first curve and length of the long chord for the second curve. And we have already calculated, or it was given to us, the length of the common tangent. So that is also all the information that we need to design. After that, we have how to lay out the curve in the field. So in this example, they have done this using the ordinate method. So that means um, that this point over here is the point T1, and this point is the point T2, starting point of the curve and the ending point of the curve. So then by using the relations of the ordinate, by using the radius, and by using the mid-ordinate and the distances from the starting point, which is given in terms of x, we can calculate the ordinates. Sometimes the x is also taken from the center as well. So it depends which method we're using. But remember that we are laying out the curves in the field using theodolite. So for the same question, now that we have all the data, we can apply the uh, the, the method of laying out the curve in the field using the deflection angle. So if you remember the Rankine's method, the equation is given. In that, you just have to input the chord length, the interval at which you want to lay out the points, and using that method, we can find out deflection angles. And the total summation of the deflection angles is equal to 5 by 2. So that's a check. So you can apply the same method over here. You can draw the table like we did in the simple circular curves, the table to lay out the curve in the field. In that, you would have the deflection angles for different points. You would have initial subchord or the final subchord and the other chords, and then the angle to be set out on the theodolite by adding up all the previous angles. So you would follow that method. So that is it for the first reverse curve in which the two straights are non-parallel. And in the next lecture, we would do the procedure in which we have two lines which are parallel to each other.